We can again use some segments for the Simpsons 1-3 rule as well. Instead of using a single Simpsons rule, we can have a composite Simpsons rule by dividing the range or limits into segments. Then we can get better results. So here you can see 1, 4, 1 is the formulation results. If you remember, the formulation was this. And we are just applying the formulation repeatedly at each segment. So we have one segment here, one segment, another segment, another segment, another segment. Each segment needs to have 3 points. 1 and 2 are like the ends, and 1 in the middle. So these goes for 1, 4, 1, 1, 4, 1 from in the formulations actually. The first one 0 to 2, then the second one 2 to 4. You can see here 2 to 4, then 4 to 6, and to n minus 2 to n. This is the formulation. If we group them all together for an equal h, we have fx0 here, the beginning here, this one, a actually, fa, then fx n here alone, b, fb, and in between points, the odd ones, 1, 3, 5, are multiplied by 4, summed and multiplied by 4, and the even ones, 2, 4, 6, they are also summed but multiplied by 2, and all of it is divided by 3 times n. N is the number of segments, and b minus a. And if we get the approximation error for this, it will be the same, b minus a5, the mean of 4s, but here the only difference is 180 n to the power 4, because we have n segments, now we have n to the power 4, and this value is changing compared to the single application of this. And this f mean value now, if you can get the derivative and integral, then you use that in the mean. But if you cannot get the integration of the fourth derivative, then you use the summation, because we have n number of segments. For n number of segments, we have n number of means, and sum them and divide by the number of segments to get this actually. So 2 options. This is total f4s for each segment, divide by n. We can show like this, or integration for each segment though. For example, x0 to x2 f4 x divided by b minus a. Let's check this in an example and see how it works in the following slide. Now here we have example 21.5, composite Simpsons rule application for this function again, but we want to use n equals 4 segments for the composite rule. And recall that the exact integral value is 164 again, and the bounds are 0 and 0.8. This is the formulation for the composite Simpson rule, and this is the error approximation. So let's check the results. Because it says n equals 4, let's first find the h value. If n equals 4, then h is b minus a divided by n, meaning that 0.8 minus 0 divided by 4, which is equivalent to 0.2. So now we will find the x values inputs using this increments, 0.2 increments, starting from a. So a equals 0, then f, sorry, not start with the f, let's start with the x. x0 is 0, and fx0, which means 0, is 0.2. And if x is, so let's increase it from here maybe. For x1, we increase it by x0 plus h, which becomes 0 plus 0.2, 0.2. Then f 0.2 is equivalent to 1.288. x2, x1 plus h, which is 0.4. f 0.4 is equivalent to 2456. And x3, x2 plus h, 0.6, and f06 is 3.4 464, and x4 is x3 plus h is equivalent to 0.8. Then f0.8 is equivalent to 0.232. So let's use all of these in this equation here. Then I is equivalent to b minus I 0.8 minus 0 times, let's sum them all. Fx0 is this 0.2 here, and 4 times odd values, so n is 4 here, which means up to 3. So we have 1 and 3 actually. Then we will get 1, this one, and 3, this one. Sum them and multiply by 4. 4 times 1.288 plus 3.464 parentheses, plus 2 times the summation of the odd numbers, so n minus 2. This is 4 again. 4 minus 2 equals 2. So up to 2, just 2. Use this. Then plus, so 2 times 2.456. And finally fxn, which is this one, plus 0.232, divided by 3 times 4 n segments, and I is from here 1.623467. You can see we got closer to this much and much better. So if we want to calculate the true error with these, ET is equivalent to 1.640533 minus 1.623467. ET from here is very small, you can see 0.017067. And if you calculate the percentage error by dividing this by this, the error is 1.04. It's almost 1% error, so it's very accurate, seems. So let's say we don't know the exact value, and we know that we can find the approximation error using this. How can we use this? Simply we need to find this f fourth derivative mean value, and we already calculated this in example 21.4. You can go ahead and check that, how we calculated it. You can use the same value from there, which is minus 2400. Use that there, here. Then EA becomes minus 0.8 minus 0 to the power 5 divided by 180 times 4 division to the power 4 times the mean value. This is this one, 2400. This is from example 21.4. You can check that, the single application of the Simpsons 1-3 rule. And the result is 0.017067. So again, it's the exact same result. Why? Because again, so this h has the 5th order and the function has the 5th order, then we will get the approximation error exactly the same as the true error. So this equivalency doesn't mean that we will get the exact integral because we have an error. Close, very close. But we will have an exact error result because we have this equivalence of the order with the error order. Okay, this was the important part of this, and you can solve it again if you want to have practice. And this is a very good application of the Simpsons 1-3 rule. And 1-3 rule is always the priority because it gives a very accurate result compared to trapezoidal rule especially. And it needs only 3 points. For composite, of course, we have more points, but for one segment, we need only 3 points. So that's very good. We compare the Simpsons 1-3 rule and trapezoidal rule in this slide. And the composite Simpsons 1-3 rule is very accurate. We mentioned this in the previous example as well for the 1-3 rule. And for this reason, it is considered superior to the trapezoidal rule for the most applications. And we prefer this over trapezoidal rule. However, it is limited to cases where the values are equally spaced. So this is important. If we have equally spaced values, it is usable, but the trapezoidal rule, especially the composite rule, can also be used for non-equal spaced data easily. Further, it is limited to situations where there are an even number of segments and an odd number of points. This is very important. For the Simpsons 1-3 rule, we need an even number of segments, two numbers. So for one single application, that's okay. We only have one segment. Actually, not one, we have one segment. Even in that, we have two segments, n equals 2, which gives 3 points for single application. But we cannot use n equals 3, we need to use n equals 4, for instance. 5 points. So 2, 1, 3 rule. And n equals 6, etc. So we need an even number of segments, which means odd number of points. If we have a odd number of segments, this is not usable. We cannot use Simpsons. Consequently, an odd segments even point formula. So this is even segment formula. This means we have n equals 3, n equals 5, etc. For these, we can use Simpsons 3-8 rule. And 3-8 rule is a quadratic fit. We will show it in the following slides. It's a higher order than this one, but still the error degrees are the same. So it only needs like 4 points. That's why we have odd segment for it, and use in conjunction with 1-3 rule to permit evaluation of both even and odd number of segments. We can use them together. So for some parts which has even segments, we use Simpsons 1-3 rule. For the segments which has odd numbers, 3-5, we use Simpsons 3-8 rule.